Okay, some of the older style valves. This is a thing called the Saunders valve. The Saunders valve used a rubber diaphragm. The rubber diaphragm is here. Used a rubber diaphragm or a flexible diaphragm, and what happens is this part here pushes that downwards onto the weir and seals it up. Here's an opened up one, and the rubber diaphragm is here, and this is a look at the base of it, and it gets pushed down, the rubber gets pushed down onto this weir which goes across and seals it up. The nice thing about the Saunders valve, which is nicer than the globe valve or the butterfly or the ball, in fact, or any of them, is that the diaphragm here actually is a seal. There's no way that the nasty crap inside here can get out, because it can't go past the diaphragm unless the diaphragm breaks. The problem with the Saunders valve is that the flexible diaphragm soon stops being flexible. Especially if you've had it shut for a long time or open for a long time, it gets a memory. And then it's really, really hard to get it to control. So Saunders valves aren't used that much anymore except in special applications. Here is a pinch valve. Now I'd like to know if any of you had experience with pinch valves. Okay, a pinch valve is another valve, another one of the many valves that were designed, primarily were designed for small applications. The nice thing about a pinch valve, it's like the Saunders valve, is if you've got nasty stuff on the inside, it can't get out. There aren't any seals anywhere. There aren't any seats that it can work its way past or anything like that. It's basically a big rubber pipe, and this is the rubber, oh, I didn't show it yet. So it's a big rubber pipe here, and what we do is we pinch the pipe shut. There's a couple of ways we can pinch that pipe shut, but with the larger ones, the way we basically pinch it shut is by having two pieces of metal. These are the metal, there's one there and there's one on the underside, and these pieces of metal are called deformers. And you push those two metal deformers together and it pinches the pipe. Easy. They work quite well, except for if you get any sort of grit or nastiness. If you get grit or sand on the rails, there's a rail down each side. If you get grit and sand on those rails, they seize up. If you've had it shut for a long time, just like the Saunders valves, the rubber tube gets a memory. So if you've had it shut, so here's one, and it's shut, so I've had it shut for a long time, and what I'm going to do is I'm going to open it, so I move the deformers away, but the rubber just stays shut, because it's remembered where it was. It's basically sticking there and it's going to stay. They do also sometimes burst. If you put mineral sands through, some of the mineral sands have got crystals with very sharp edges on them, and those sharp crystals just cut away things like rubber. But they have the advantage that until they burst, the stuff stays on the inside. Now I want to talk about a couple of problems that we get with all valves: cavitation and flashing. Cavitation and flashing are things that occur when the valve is nearly closed. One of the main causes of cavitation and flashing, of course, is that we bought a valve that was too big. If you buy a valve that is too big, you'll tend to be opening or closing it only around the very short part of its stroke, and so it will be nearly closed. Another cause of cavitation and flashing is if the valve leaks. If the valve leaks in any way, then you will get cavitation and flashing. It's caused when thin streams of water go from, or liquid, go from high pressure to low pressure. So whenever you have a high pressure to low pressure situation, which is what you get when the valve is almost closed, you get these two problems called cavitation and flashing. Now, other things, other places where you get cavitation and flashing, it's not unique to valves. Other places where you get cavitation and flashing is pumps and propellers. I think I may have spelled that wrong. Is anybody familiar with cavitation and flashing on pumps or propellers? Okay, now you know when a pump or a propeller is cavitating because it makes a noise. And that is, we're going to go into what is exactly occurring there. What's occurring is, if you reduce the pressure of, actually I can show it on here, if you reduce the pressure of a liquid, so here's the liquid going through the valve. It gets up to the plug, and then just here it goes through the plug. Now the liquid pressure now goes very, very low. If you reduce the pressure of a liquid beyond a special line, which is called the vapor point, then that liquid turns into vapor. So we've reduced the pressure to such an extent, basically, we aerosoled the stuff through there, and it vaporized. So we reduced the pressure beyond the vapor pressure point, and it turned into vapor. It turned into bubbles. Now, with cavitation, we then repressurize. And we repressurize to above the vapor pressure point. And so we turn back into liquid. With flashing, we don't repressurize enough so that we don't turn back into liquid. Flashing is permanent formation of vapor. Now this is what happens with cavitation. A small bubble forms. The bubble then goes along and maybe gets a bit bigger. Then it repressurizes. And when it repressurizes, the bubble implodes. The bubble implodes. Now, the bubble doesn't implode nice and gently and slowly disappear without bothering anybody. The bubble actually implodes, bang! It implodes at the speed of sound. And so what it does is, it makes a little tiny sonic boom. And each bubble imploding makes a tiny sonic boom. And then you get these shock waves spreading out from the bubble. And these shock waves spread out, you know, like tiny sort of Star Wars special effects shock waves. It goes coming out. Now they very, very quickly dissipate away to nothing. You know, they very, very quickly just dissipate away, these shock waves. However, if it happens to have occurred, if it happens to have imploded next to a piece of metal, there's enough energy in that shock wave to vaporize a cavity out of the metal. It just carves a little chunk out of the metal, as if somebody has attacked the metal with a tiny weeny little ice cream scoop. That's why it's called cavitation, because it makes a cavity. Now, a slightly different thing can occur if the air bubble happens to be a little bit flattened. If the air bubble happens to be a little bit flattened, then when that implodes, it causes what's called a liquid microjet. And you have this liquid microjet. It's minuscule. it would be minuscule compared to a human hair. It's a tiny, weeny little microjet. However, it's got 700 megapascals of force behind it. That microjet, if it happens to be near a piece of metal, will just chuck that metal away. It will just make a hole in that metal. You can't fight 700 megapascals. It's like a tiny weeny little liquid hammer, little jackhammer, and it just knocks a piece of metal out. So cavitation will either cause these cavities like this or rougher cavities like this, depending really on the shape of the air bubbles. Either way, what's happening is it's chewing the metalwork away. So cavitation is a two-stage process. The bubble forms, and then the bubble collapses, and the bubble causes lots of destruction. Here are some pictures of cavitation damage to valves. This is the plug of a plug and seat valve, and it's just, as you can see, it's just been eaten away. This is classic cavitation damage. You see these tiny little craters. That's why it's called cavitation, because it causes craters. This is damage to a cage on a valve. And once again, you can see, I hope you can see, lots of little craters. This is damage to a plug on a valve, and it's been caused by a slight leak. The valve has very slightly been leaking, and the tiny flow has come through, and cavitation has occurred. And as it's come through and cavitated, it's dug elongated things out of the plug. This is cavitation that has occurred in a ball valve, and it's just eaten these things away. Those holes didn't start like that. Those holes were originally holes like this. And there was another one here and another one here. And those holes have been eaten by cavitation. Oh, and by the way, this shaping on the casting, that is not how the casting started. The casting was smooth. This has all been pitted by cavitation. So that's the sort of cavitation damage you will see in valves. And the root cause is probably, well, it's either that the valve is leaking, or you bought the valve that was too big. The valve's too big, and you're working in the 0 to 5% region of control, and so you're constantly aerosoling the jet through, and you're getting vaporization and cavitation.